knowing what the position correction is on this guy, then we can determine the one on the pace airplane. Nice thing about a pace, you can go to altitude to do this, where the air is generally always smooth. Well, we essentially talked about that. Well, there's several other methods that have been used. Trailing bombs, trailing cones have been used with assuming zero error, but that's not always the case. Generally, when I worked at beach, we calibrated those instruments themselves. We would take the trailing bomb and go out and drag it across the speed course. And so you had to be careful doing that on a speed course because you might get the bomb underneath the fence if you were a little bit too low, and not a good thing. Well, technology is being made a lot easier, or made this one a lot easier with GPS. I started looking at GPS for airspeed calibration in 1990. At that time, there wasn't enough satellites up there that you didn't have to wait until you got 3 in view. Now there's a full constellation and you always got satellites in view. But when I first started doing airspeed calibration with GPS, you had to wait until a certain time of the day when you had 3 at the right angles in order to do it. But you know, one of the ways of calibrating this thing is, and the nice thing about this is you don't have to fly real low where it's bumpy. We'll do this method here in the class. That'll be the next flight we'll do. We'll go to altitude to do this. And I've used it for about 25 years now, I guess. Or 26 years with pretty good results. Nice thing about GPS receivers, in addition to the ground speed, they also give you the track that you're making that ground speed over. That isn't necessarily the same as your heading because of winds. And the ground speed is the most accurate thing on a GPS. It's good to about the 1/10 of a knot. Why is it the most accurate thing? Well, here's where I used some of my math. I said, wait a minute, ground speed, even if, let's say this is a air position, and your position was off by, let's say, a mile. Well, this position line is the same. Well, if you take the slopes of these 2 lines, and again, I have a hard time drawing on the board, but if you take the slopes of those 2 curves, they're the same. Okay, so again, there's your first derivative. That's I say about as much of math as I remember, but that allows you to have a very accurate ground speed. The ground speed is along the track. Your airplane heading is probably different than the ground speed. And so again, you use trigonometry to get the ground speed along the track into the ground speed of your heading, the direction you're flying. And then you use the data reduction scheme of the old speed course method, which has 5 steps, which is the other thing. Now, there are other methods out there using GPS. One of them flies a triangle. it has 25 steps in the data reduction. Anytime I can take 5 steps instead of 25 steps, I'm going to do it. Number one, I'm lazy. And number two, I'll guarantee you in 25 steps, I'll make a mistake. Okay, so I happen to like my method better than some of the others that are out there. Well, here's that, what I just tried to draw you on the board. Doesn't matter, see, it really doesn't matter. These two slopes are the same, even though the actual position. Folks first started out trying to use the position like a speed course. Well, you know, it may be different between here and the other end. Although it's still pretty accurate, it's not as accurate as using the ground speed, since it's the first derivative of the position. Advantages, well, you can perform it at altitude with smooth air, stabilize the airplane on a cardinal heading at the test airspeed, remain stabilized long enough for the GPS to update and attain a steady ground speed, which usually is less than 10 seconds. Okay, and then you record the following data: GPS ground speed, GPS aircraft track, your observed airspeed, your observed pressure, altitude, and temperature, and the airplane heading. That's the data you take. Then we do a 180 return to same airspeed, record the same stuff. See, this is just the speed course taken to altitude, okay? But we get, instead of flying a known distance to get a ground speed, GPS gives us that ground speed. So we just take the average again between the one we go in this way and the one we get coming back this way. We got it. And it doesn't take near as long, because all I have to do is be stabilized long enough for the GPS to update, turn around the other way. And nice thing about it is the first one you have to turn around. And after you get this one here, you just go to the next speed and then make a turn. Okay, after you get that speed. So it goes very fast. I can generally calibrate a complete system, both flaps up and flaps down, and you do get a difference, okay? I can calibrate the complete system in one flight of an hour and a half. Where the old speed course method took forever. But you can see, it's just based on the speed course method. I didn't really reinvent the wheel. Well, what you do with the data, apply the instrument correction, determine the angular difference, I call it theta in this case, between the heading and the ground track for each heading. Ground speed component along the heading, which is just a cosine of that angle, times that, and that gives you the ground speed corrected. Determine the atmospheric density ratio, and here's the equation to do that. Or you can use altitude tables if you happen to have one. When I first started, we didn't have computers that would solve that equation. Somebody had to do it by hand. People were a lot better at math back in those days than I am today, let me put it that way. But delta, that's the pressure ratio, okay? 1 minus 6.87535 times 10 to the minus 6 times the indicated pressure altitude, what you read off the instrument essentially, after you corrected for the instrument error, raised to the 5.2561 power. That is the equation for pressure altitude, okay? Or delta pressure ratio, I'm sorry. You can solve that today probably with your cell phone. Then you determine the atmospheric temperature ratio, theta. Now I'm using two thetas here. Forgive me. You know, one of our problems in engineering is we ran out of alphabet and Greek letters. And we end up using them more than once. And you go to one class and theta means one thing, and you go to the next class and it means something else, and you go to the third class and it means a third thing. Before long, Anyway, this is 273.16 plus, again, the instrument corrected ambient temperature, which you're going to read in the airplane, okay, divided by 288.16, and that is in degrees Celsius, by the way. And once you have those two values, then we put delta, which we got from the first equation, over theta, which we got from the last one, and that gives us, and take the square root of it, and that gives us square root of sigma, or square root of the density ratio, and then the calibrated speed is equal to the ground speed corrected times the square root of sigma. And then we add the two together, from each heading, divide by 2, and then depending on whether it's above or below the instrument, whether we're going to add or subtract. But anyway, we take the indicated speeds from each one, divide by 2, hopefully they're the same. They may not be. And then the position correction, the difference between the two is the calibrated plus or minus the indicated, depending on what side of, whether you're above or below, okay? And then you plot delta VPC, this correction, versus the instrument error, and that is the thing for the airplane. Takes the instruments completely out of it. That is the airplane calibration. Okay, so you've got an instrument calibration, you've got an airspeed calibration for the airplane. You've got an instrument calibration for the instrument, and you have an airspeed or an airplane calibration for airspeed, and you have to put both of those together to get the actual value. Okay. Questions? I think that's the last one. Yep. This is what we'll do on the next flight. In fact, if you want, since we didn't get to fly today, when we do fly next week, if you want to do a couple for practice, we can do that. Okay? That'll allow you to get a couple of points, just so you can go through the procedure and see how it works. Okay, I think it's lunchtime.